Okay. All right.
Yeah. So good morning, everyone. And today we start our morning with a hands-on session by Tim Hamilton. This is on integral field spectroscopy. And Tim has been with us from the very beginning with Astronomy for Archival Data, as well as AstroSprint 1 and 2, Discovery and Enterprise, and now we are on Next Gen. So welcome, Tim. Happy to have you with us. And over to you. Yeah.
Okay. Pardon me, I got a little bit of a cough here. But so I'm glad to see everybody in here again, and I hope that you've been able to have some who are in person this time. I'm sorry I couldn't be there myself, but it was a bit far to fly in for one day. So what I'm going to be talking to you about tonight, this morning for you, is on what's called three-dimensional spectroscopy or integral field spectroscopy. And it is a relatively new technique. I say relatively for my career. This became feasible about 20 years ago, or at least started to become a little more possible and common about 20 years ago. So it's still developing. And this is for those of us who are in optical, visible light astronomy, this is really a powerful, fascinating new way to approach collecting astronomical data. It's a combination of a spectrum and an image. So let me start this up here. Let me see about sharing screen. Okay, now let me think where I should put this. I'm going to have this. Let's see. I should put it with the PowerPoint. I'm trying to see the best way to do that where I don't simply have just a whole screen on there. Ah, there we go. I have way too many files open right now. Okay. All right, can everybody see that okay? Speak up if you, Priya or anybody, if you can see the main slide there by itself.
Yes, sir.
All fine. Yeah.
Okay, great.
You're on the presenter mode. You're on the other one, which shows both, right?
I'm sorry, say that again?
I said you're not in that presenter mode. You're in the mode which shows both slides. You know, the present one and the next one.
Okay. Let me try. What I'll do is I'll share a single screen rather than the application. That's why I needed to check.
Yeah, this is, yeah.
Okay, now you should see only one slide. Is that right?
This is perfect.
Okay, good, good. All right, now I'll apologize that I don't have, this is not quite as fancy looking as I usually expect for myself. I put the slideshow together a little bit late, and unfortunately I do not have the new chapter of the book written, but I have tried to write out a step-by-step procedure in PowerPoint here, which I'll make available to Priya to share with y'all. So, the idea of an integral field spectrograph is that you have an image where every pixel gives you a spectrum. So let's give some examples of what these are like. There are 2 or 3 different ways of creating an integral field spectrograph. The first is that you can use optical fibers. One example of this is the Sloan Digital Sky Survey and their MANGA instrument. Here's the Apache Point Observatory, home of the Sloan Digital Sky Survey in New Mexico. There's the telescope itself. And now, if you imagine where the light is coming in through the aperture, reflects off of the mirror, the primary mirror, onto the secondary mirror, and then onto the focal plane. you're used to the idea that you would put the camera detector there at the focal plane. And they do most of the time. But once they've taken a photograph of that region of the sky, they go back and they identify objects that may be of interest from their colors. They could be stars of a particular type. They could be galaxies that have a particular type. And what they do then is they take an aluminum plate, which is made to fit the size of the focal plane, and they drill holes in it and they attach optical fibers to the locations of where certain galaxies or stars are focused. And they take those fibers and they arrange them into a way to make a vertical line, which imitates the slit of a spectrograph. Here we see, in fact, the aluminum plate on the back side with the little plugs where the optical fibers go in right there. Those then feed into the spectrograph. Actually, this is showing them going from the plate to what's called the Cartridge Box. Into a, well, it's a guide that arranges all of those individual optical fibers into one long row that will be then shined onto the diffraction grating, so that then that will be captured by the detector, the camera, and then you will get maybe I don't. It depends on the survey, but anywhere from a few hundred to maybe 1,000 individual spectra side by side of different objects in that field of view. So this is a fiber-fed integral field unit, or I prefer to call it an integral field spectrograph because that explains what it is. But the more common term these days is simply integral field unit, or IFU. So you can use the terms interchangeably. So manga has this interesting arrangement here where they've been using those optical fibers for individual galaxies or stars where each fiber sends a single beam of light into the spectrograph. But with manga, the integral field spectrograph, what they want to do is have several different fibers that cover each galaxy. And so what they do is they have the plug for that, and you can see it here held in a hand. And at the tip end of the plug, you see this hexagonal shaped cluster of optical fibers. If we zoom in on that, we imagine it in the image plane of the focal plane, of the telescope, then perhaps you would have maybe a spiral galaxy focused onto the tip of this plug here. And that galaxy then would cover many different, I believe it may be 127 individual fibers from one end to the other. Each of those fibers has a spectrum for it. So you get a rather crude spectral view of that galaxy. The imaging would be a little bit crude in this way, but the spectral view can be actually quite sharp. If you take a look at the spectrum of the center of the galaxy here, you might see something like this, going from 4,000 to 10,000 angstroms. That is from the violet into the optical spectrum out into the near infrared. While if you look at the edge of the galaxy here with fiber number 2, you might see something very different. Okay, number 1 there is showing strong emission lines, possibly a little bit broad here with that maybe H alpha. And while fiber number 2 is showing the 4,000 angstrom break in the spectrum of a galaxy. This is distinctive of older populations of stars. That break gets larger the older they are. That's the H and K Fraunhofer lines created by calcium. And then a declining spectrum over to the into the red side there. Okay, with narrow spectral lines that may be characteristic of star formation. Okay, that's just an example of what you might get there. Again, for scale, you can see how this is in the held by 2 fingers. These are very, very small fibers. And each fiber will carry the light with a little bit of loss, a little bit of, you do wind up with less light coming into the spectrograph than you do starting due to the fibers absorbing some of it. But this is a very convenient way to get a whole lot of different objects observed at the same time. If you take a look at the image that was first taken by the Sloan Digital Sky Survey of that galaxy, we can overlay the footprint, the image footprint of the MANGA integral field spectrograph over the top of that. And they sized it in order to fit galaxies of typical sizes at a certain redshift there. Okay, so that's one method. Now, you could focus the light directly onto the ends of the optical fibers. A second method related to this is to use an array of what are called lenslets, that is, small glass lenses, to focus the light onto each fiber separately, and then to run it through the fiber-fed integral field unit. This is one which is used by the European Southern Observatory. So you have a micro lens or lenslet array of small square lenses. Each one then focuses light on a single fiber down beneath it. By doing this, you don't have the gaps between the regions covered by each fiber. That is, if we take a look back at MANGA here, we can see because we have round fibers in a hexagonal array, we wind up with gaps between each of the fibers. In fact, a hexagonal array is the closest that we can pack any set of circles. So this is the most efficient way of filling that space. But because the fibers are round at the end, they cannot be packed without some gaps between them. The lenslet technique avoids the gaps for the most part then. And so we wind up with less loss of the skylight. Okay, and so what they did here, they had 20 individual fibers going there. The fibers are arranged into a slitlet, they call it, but that's really simply imitating the slit of a standard spectrograph, what's called a long slit spectrograph. And then that light is brought into, is focused by a lens onto the diffraction grating. The diffraction grating disperses the spectrum, and then we have another lens to focus it onto the camera, which is really acting as a spectrograph detector in this case. And again, each one of these fibers here will have a row. Its spectrum will appear on a single row up here, maybe 2 pixels across or something like that, depending on exactly how they space it. And then the next fiber will produce a spectrum the next row below, and so on and so forth like that. Then in software, after the fact, you can split the camera plane up into the individual spectra and store them separately. Here's another diagram of the European Southern Observatory lenslet array. A photograph there in the upper right, and then a more careful schematic here in the lower left. So the light comes in, again, it's plugged into the board like that. We have a prism that simply reflects the light with fewer losses than if we were to use a mirror. And then we have the fiber holder like this here. Okay, now a third or second, depending on how you count it, technique is to use what is called an image slicer. This is an interesting one. The technology is harder to do without a lot of custom equipment, but it provides for some very good image transmission, image throughput with fewer losses. The idea is that you have an array of little mirrors, each of which is angled at a different angle. And then they reflect, you focus the light, you put this in the focal plane, you focus the light onto this array of the image slicer, and then each row of it is reflected at a different angle to a different part of the spectrograph then. This is true of the European Southern Observatory's Muse spectrograph, M-U-S-E. So the idea is if we have an image that would look like this, and it's focused onto the focal plane with this view, then our slicer takes each of these rows, 1, 2, 3, 4, 5, and 6, like that, sets them out separately, and then each one of those is focused onto a region of the diffraction grating, so that we wind up with the whole spectrum of each of those rows there going down vertically. So we have several pixels across for this slice of the image. And then each one of those pixels winds up with a whole spectrum here. And then we do that we just arrange it side by side like that. Again, in software, we combine each of these to create what's called a data cube. The idea of a data cube is that our X and Y axes show us the image space, while the Z axis is the spectral space arranged by wavelength. So we wind up with a complete image of this part of the sky at every wavelength covered by the spectrograph. We can either look at the whole image at any given wavelength, like this, or we can take one region of the image, or the entire image, and produce a two-dimensional spectrum like this. Actually, I guess that's more of a one-dimensional spectrum here, where we simply have intensity versus wavelength on it there. And I'm going to take you through those techniques tonight. Just for fun, this is the back end of Muse. What you're looking at are not optical fibers like you had in MANGA with the Sloan Digital Sky Survey, but rather these are the cooling pipes to keep the whole thing cryogenically cooled, where the detectors are much more efficient, especially for the infrared part of it there. It needs to be kept well below 0 degrees. At nighttime, with this attached to the telescope, you can see the telescope up here above it, and you can see the Muse camera, the Muse integral field spectrograph down below here. It really is a neat arrangement. I haven't gotten to use this one in person, but I've been working with data from it. There are other integral field spectrographs out there, and I'll give you links to a few of those at the very end of the talk. Okay, how can we view integral field unit data? Well, the thing that I recommend using is the Smithsonian Astrophysical Observatory's DS9 software. The original version was called SAO Image, Smithsonian Astrophysical Observatory's SAO, so SAO Image. Then some years later, they came up with a new version of it, which was called SAO TNG for the next generation. Now, if you've ever watched Star Trek, you might have heard of the Star Trek The Next Generation, which came out in the 1980s and 1990s, and I guess early 2000s. And they were obviously kind of Star Trek fans. And in fact, they made a Star Trek logo shape for the new SAO image program. Then they came up with a third version of it, which they simply called DS9. Which at this point, they're not even pretending for it to stand for anything other than the Star Trek series Deep Space Nine, which was often abbreviated DS9. So that's the current version now. They've gone through several iterations of it, and it's able to handle these data cubes from the integral field spectrographs. So I'd recommend getting SAO DS9. It'll work on every computer platform, and it's free. That's actually one of the great things about professional astronomy software, is that it is almost all of it is free. Okay, I'm going to give you an example of how we can use this using the Keck Cosmic Web Imager, which my colleagues and I had gotten some data from back about a year or so ago. Right here, we have a photograph taken that we took, in fact, with the Hubble Space Telescope. This is of a weird gravitational lens that I discovered. And here we see a cluster of galaxies, the yellow to orange colored blobs or galaxies that are in the foreground at a redshift of about 0.5. Those that are these white ones here, and here, and up here are we're looking at a spiral galaxy much farther away, about a redshift of 0.7 or 0.8, so much farther back. And what we see here are 3 images of it. 1, 2, and then up here is a third one. Okay, and we see a whole lots of other things that also may be gravitationally lensed. Let's circle these so that we see them clearly. Now, what I'm going to do is, I've got these 3 circled, and I'm going to show you the view through the Keck Cosmic Web Imager. All right, here I have the DS9 program. On the left-hand side, I'm showing a black and white view that I just showed you of that color picture. We've got images 1, 2, and 3 right there, or let's call them A, B, and C, which is how we've labeled them. And I've got a 4th one circled. We're going to get to that a little bit later. As soon as you open up a 3-dimensional data cube in DS9, it pops up with this extra window, which it just says AWAV, and that stands for wavelength. I don't know what the A means, but the rest of it is wavelength. And what it's showing you is the wavelength in angstroms. Here we're looking at 3,227 angstroms is the first wavelength available. We can go all the way out to 5,798 angstroms on the right-hand side, and that'll appear on the right when we scan through. Now, we can grab this knob here on the slider and simply slide it from left to right or back and forth and choose any wavelength we want, or we can enter the wavelength we desire in this field here, or we can hit play, which will step through them maybe once per second, or you can adjust the speed settings. We can stop, we can go to the previous, the next one, the first one, or the last one like that. Okay, now what I'm going to do is I'm going to scan through these wavelengths here. You see the still image on the left, and you're going to see a smaller field of view for the Keck Cosmic Web Imager on the right, but I've lined up those same 3 components, those same 3 images right here. So the Keck Cosmic Web Imager covers about that region there. Okay, now let's take a look as I play a little video I've made. All right, I click on that. Now, look how poor the image quality is on the Keck Cosmic Web Imager. The pixels are very large. On the other hand, we can clearly make out the blobs for these 3 galaxies that we have circled here. There we go. We saw a spectral line come out on all 3 of them. Now we see some other spectral lines. Let's run through this again. If you go through it rather quickly, the static, the noise is sort of smoothed out to your eye, and you can see trends. I can even make out other galaxies in that area there by things like you can see this up here in the upper center. That's going to be that bright galaxy right there. We're seeing the continuum. We can see a bit of this elliptical galaxy here. So that right there is going to be shown over here. But it's a red galaxy, and so when we get to longer wavelength is when it comes up. And now we start to see it about here. Okay. Now, you'll also notice some parts where the beginning or the end, and sometimes in the middle, the whole screen looks staticky, and that's simply from defects in the camera. Sometimes that's also from the emission and absorption lines of water in the Earth's atmosphere, and we'll get to that a little bit later. Okay, now let's go from there, and I'm going to add on a special look at this little thing right here. You may be able to just make out a little blue arc, and it turns out that this is another gravitationally lensed object, and let's see what we see here. This is what's called a Lyman alpha blob. It is a glowing ball of hydrogen gas, glowing primarily with the Lyman alpha emission line. That's the bright ultraviolet line of hydrogen, from the first excited state down to the ground state. We don't know exactly what causes Lyman alpha blobs. It could be from a quasar, it could be from a cluster of galaxies, or from star formation within a galaxy. And but we don't really know for sure right now. So what I'm going to do is I'm going to look at this in a different way. Rather than look at the whole image as I scan through the wavelengths, I'm going to look at one wavelength while I move to different parts of the image. So what you can do is you can take these green circles here are called regions in DS9. If you create a region, you can look at statistics on it, the average brightness or the maximum, the minimum brightness, things like that. But you can that allows you to do photometry in a very simple and crude way, but it works. You can also use it to plot the spectrum of that region of your image. So whenever I create a region here, the spectrum will pop up in a separate window like this, the one-dimensional spectrum. Okay, now what I've selected is this region right here, and I have moved to a wavelength of the Lyman alpha emission, and you can see how bright that region, that arc is right there. Again, because these pixels are very large, it doesn't really have the clear shape that we had from the Hubble image, but we do have very good spectral resolution. Now, the neat thing about this to me is that if we move from the top of the image here at the north, and we slide it down to the south and off to the east a little bit, we see a different wavelength for that emission line. Now, again, this is the wavelength in angstroms. Normally, the Lyman alpha emission line is, and I should remember this right now, 2,700 angstroms, something like that. One of you will probably know better than I do. Pardon me. When we
1215, I think, right? 1215.
Okay.
1,200.
1,200?
I'm not. I'll just check.
Okay. So this shows you just how redshifted this source is. This is at a redshift of about 3. So we have it at a wavelength of about 5,100 angstroms. Now, as I slide this down, you'll see that because it's brighter here, the emission line will. Pardon me?
To interrupt, but it's 1215. 1215.
Okay. So as I slide it down here, we'll pick up more of the light, and that will make the emission line go brighter. But also, the thing I want you to pay the most attention to is we'll go from blue on the left to red on the right, or vice versa. Okay, so let's watch this. So I grab it there, and I drag it down. Now, look how the wavelength, the peak goes to the redder side. And as I go back up, the peak goes to the bluer side. And I believe every dot in that there is about 1 angstrom apart. So we have very, very good spectral resolution. What we're seeing is Doppler shifting. Not just the Doppler shift of the entire source, the average of it. As I told you, its redshift was about 3. But rather the Doppler shifting of individual regions within the source. That is, we're seeing the motion of the gas moving toward, well, it's all moving away from us, but relatively blue shifted on the upper part and relatively red shifted on the lower part. This means one of two things. Either it is rotating, with one side moving towards us and one rotating away from us, or we have outflows where we have a flow of gas towards us and on the backside a flow of gas away from us. Although in that case it would be, if it's opaque gas, we would not be able to see this part on the backside. So I think rotation is a little bit more likely. Okay. Oh, we'll go through that one more time and then I'll go on. Okay. Now, what you can get out of what I've shown you so far is simply a quick look at the data. But with more sophisticated processing, you can come up with all kinds of things here. For example, using the manga data, they automatically process things like, I haven't looked into the manga data very much, but what they show on their webpage is some of these data products here. They can map out hydrogen alpha emission lines, which traces star formation within the galaxy. So if you compare these regions here, these are the ones that show strong star formation, and we can compare them with the image and see that, yes, these are lying along the spiral arms. Not so much on this outer arm here, but on this inner arm, for example. Also, we don't have much star formation along the galactic bar running through the center, but we do have star formation at the very center. We can take a look at the velocity of the gas and of the stars here. Now, the stars, that may be a little bit trickier on that there. The gas, at least, if you see a single emission or absorption line, then you might be able to make it out. But either way, you can work with emission or absorption lines. And so if we take the redshift, the motion and the redshift of the center of the galaxy as the average, then we can see on this side, the emission lines are all a little bit redshifted, and on this side, they're all a little bit blue shifted. And this tells us it's rotating with the lower left-hand side coming towards us and the upper right going away from us. And the same is true for the stars. Notice, though, that they have had to block up this into several regions there to be able to get good statistics on it. Finally, they also show what's called the D4000 index, which is a marker of it's the H and K 4000 angstrom break there. And the larger that is, the older your stars tend to be, although you've got to be careful with dust and other things like this. But anyway, you can use it as a proxy for the stellar age. Now, I don't know what their scale is for the color in here, where I'll be able to tell. Probably the inner part is going to be older stars, and the outer areas are younger stars. That's typical anyway. Okay. Now, there are many kinds of projects that you can do with an integral field spectrograph. Because it combines both spectroscopy and imaging, you can use it for anything that involves either, or the best thing, though, is for things that need both imaging and spectroscopy, because you get everything at the same time. So one that I'm going to show you tonight is looking at the galaxy rotation curve and getting the mass distribution of the galaxy. Another one is you can take a look at where star formation is occurring throughout a galaxy. Okay, is it occurring in the arms, on the front side of the arms, the back side, in the nucleus, or what? What about the distribution of stellar ages throughout a galaxy? Are the stars in one region older or younger than another? That also tells us something about galaxy evolution. One that I'm interested in is looking at active galaxies. You can see if there's a correlation between the activity of the nucleus and star formation throughout the galaxy. You can look at the motion of gas. So you can see whether you have flows of gas down into the nucleus there, especially when you have an active galactic nucleus, or if you have outflows of gas coming from, say, rapid star formation, a starburst. Merging galaxies could provide a very interesting case. If you take a look at merging pairs of galaxies, or a galaxy, a large galaxy, and a dwarf galaxy that's orbiting it, you could separate the components of the different components of stars in different parts of the galaxy or in different galaxies. You can compare the star age and the star formation rates from one galaxy and the other as they're colliding, and you can look for the formation of active galactic nuclei. So I'm going to take you through most of the steps of plotting the galaxy rotation curve and finding the mass distribution of a galaxy. Okay, now here, normally I would have this written up as a chapter of my observational astronomy book, but I haven't gotten to that part yet. Right now I decided it was faster to type it up in PowerPoint. So I've got that here. Pardon me. Okay, so the first thing to do is you're going to go to the European Southern Observatory Very Large Telescope website, and you're going to go to the archives, and you can select those that are observed with the Muse integral field spectrograph. Next, out of those that you find there, you want to identify those that are spiral galaxies. Now, there are a couple of ways you can do this. You could just go through the list of all the observations of Muse, and you could look up what the galaxy type is in the NASA Extragalactic Database on the web, or you can simply Google it from the name. Another, maybe definitely more efficient way is to start with a paper, a published paper, that includes a survey of spiral galaxies observed with Muse. You can use the NASA ADS, that's the Abstract Data Server. I'm forgetting exactly what it stands for. And look up keywords on that there. Now, why do I say spiral galaxies? Because elliptical galaxies have three axes to them, and they have very, very little angular momentum. That is, any given star is moving on nearly a random orbit around that elliptical galaxy. And so there's no overall motion on the average there. On the other hand, spiral galaxies have large angular momentum. That is, most of the stars are orbiting in the same direction around the center of the galaxy. So if you want to look at the rotation of a galaxy, you really want to look for a spiral. Ellipticals have some rotation. Dwarf irregulars have very, very little. Also, the spiral galaxies tend to have star formation going on, which gives you emission lines, which are easier to identify than, say, the very thin absorption lines that you might have from an elliptical galaxy. And you have, the lines are weaker there anyway. Okay. So you download the data set. Because you have so much information in each file, the files are very, very large. The smallest one that I've used so far is 2 gigabytes. And I have downloaded at least one that was over 8 gigabytes. So you need to be prepared for long download times, and you're going to have the need for a lot of disk space. For example, I can't even fit one of these things on my computer right now. This is an older computer. I've got a lot of other files on it. So I need to have my trusty SSD solid state drive. This is a 1 terabyte using USB 3 and actually USB-C and give it a fast connection to it. So it's worth it to have the external drive there. Because these are large files, if you simply try to download it in the normal way, you might, what happens if the internet connection goes out? Well, in that case, you wind up losing everything. And maybe it was going to take it an hour to download. At least I'm running it from home right now, and I can do that. And that can be a problem. So the better option for these big ones is to use what's called a download script. You see here. And that runs in a terminal window. And it's simply a set of shell commands. Now, this works on Unix computers and Linux computers. So that means Macintoshes and Linux. I have not tested this with Windows. I'm not sure if it would work or not, but you'd have to see. Honestly, for professional work, it is worth having a Unix or a Linux machine. Again, Macintoshes are Unix, and you can get a cheap Windows computer and install Linux on it yourself if you want to go a much less expensive route. But that's what most of the software is written for. Okay, now what you're going to get are 2 files, 2 image files. These are called FITS, and if you've gone to any of my previous talks, then you'll know about those. FITS stands for Flexible Image Transport System, and that's simply an image file. It's not necessarily image. It can store all kinds of information. But the important thing about it is it has header information. That means that for every image that we've got, we have a kind of a layer of the file that stores keywords. We can put in things like when the picture was taken. We can say what the target was, where the telescope was, who the operator was, other important information about the scale of the picture, how many arc seconds per pixel, and so on, exposure times, all kinds of stuff like that. So FITS is a great file format. And again, you're going to need the DS9 software or something equivalent to it in order to use that. I will note that there is what's called JS9 software which uses JavaScript, which is available on the web. Not quite as full-featured as DS9, but it will do many things. Now, you get two FITS files. The first one, the smaller one, is simply a regular image. Probably they simply took a few frames from the spectrograph and then made those into an image there. That allows you to get an overall view of what you're seeing there without having to worry about the spectral lines. The larger one is going to be your integral field spectrograph data cube, which is what we'll do the analysis on. So first start with a standard image, the smaller one. Got a hot mic there?
Tim, you need to unmute yourself. I've muted you.
Okay, I've got it. Thanks, Priya. Okay, so the first thing you want to do is simply to take a look and see what this thing looks like. Is this even going to be a usable galaxy? So you'll open the standard image in DS9, adjust the brightness and contrast to see it, and just make sure it's suitable. Let me go through this. I'm going to exit the slideshow for just a moment and show you what this is like. First of all, let's go to the archive. Let me see if I can find the archive. Okay. Okay, this is eso.org, and this is the Muse overview. They don't have a separate archive for Muse. They simply do, it's an archive for all the instruments. Let me take a look for archive here. I had it the other day. Here we go, ESO Science Archive Facility, archive.eso.org. Okay, I think what we want is raw data query form, instrument specific query forms. Okay, and so we can click on Muse here.
Sorry, Tim, but could you just cut paste the website on the chat window?
Yes.
Because I spelled archive wrong.
Okay. All right, and I should put that on my last slide for the resources as well. Let's see, I'm on page 30. Okay, not elegant, but it'll get that done there. All right, and if you don't even know what you're looking at, let's see here. I think you can simply search. Let's see if that worked. There we go. There's something. Now this is if you don't know anything whatsoever, and you can just click on these things here. And then now this is the object, that's the target there. Some of these are simply calibration, SDSS J22, whatever. That's something from the Sloan. And so you could take a look. Let's click on that, and we may get a view of it. Let's see here. Date observed 2015. That was when this was a new instrument. Program ID. You can click on that and it tells you what they were proposing. This is the proposal title. So this is a radio loud quasar. Okay, so that could be an interesting one there. And I was hoping that we would have the image preview, but we don't seem to. Nope, no image preview there. Well, that's why I had to go and do this the hard way myself anyway. So, but if you go through one of these papers that's on surveys of spiral galaxies, you can get that. Now, actually, let's click on this, and let's header. Okay, preview that. And let's request this data the new way. Okay, here we go. So it's got one file. Let's see here, Science Cube. Data, processed data. That might be what I want. Okay. Sorry, I've only done this a couple of times on here. Now, you can download it as a zipped file like that as an archive. But again, if your internet connection breaks at some point, then you might have to restart it. If you do the shell script, okay, you simply save that file. Okay, you save it like that. And when you run it, okay, if you're on a Unix or Linux terminal window, you just put // which allows you to get into the directory where you did that, and you type the name of the script and you hit enter, and it automatically goes through all the queries and downloads it, and it gives you a little, it's not really much of a progress bar, but it tells you how much has been downloaded here. And so this one is the one that I just did before tonight's talk. Okay. Now, what we get out of this then is, let's see. All right, we have these two files here, for example. Now, I'm going to hide the frames, and I'm going to show you only the ones we're looking at right now. Okay, so on the left is the plain image, and on the right is the spectrograph image. So I'm going to zoom that to fit there. In fact, let me only show one. Okay. Again, I won't go over DS9 in great detail, but if we hit scale, we can look at linear or logarithmic scaling. I prefer logarithmic. Minimum to maximum, that allows you to see the full dynamic range. It may be a little bit too much in some cases, but if you hit parameters, then you can set the low and the high pixel values to whatever you want. Okay, and you can, by clicking and dragging, you're able to adjust brightness and contrast on the fly, which is fantastic. So this shows a lot of feature in the outer layers there. Okay. But again, this is only a black and white image. So this looks like a fantastic galaxy for working with then. So let's go to the Muse view of it. Okay. Now, let me get rid of that there. All right. Well, that doesn't look like much. It looks much noisier than the other one was. And I believe the way that they make the single frame image is by combining all the wavelengths of light, which averages out all of that static and noise. So I'm going to first adjust this the same way I did the other one. Okay. About like that. Now, what pops up immediately, there we go. It says AWAV, that's the wavelength. And this is the observed wavelength in your frame of reference. So we can go from 4,749.6 angstroms, all the way up to, if I hit last, 9,349.6. So we go from the blue end of the spectrum out into the near infrared. Let's start with the blue end. I'm going to take this and scan through. Now look, it looks like you're looking at a movie that you get flickering. Now the bright flashes over the entire screen are simply glitches in the computer. but we can see how it gets brighter and dimmer in distinct ways. Ignore those flashes. And sometimes we see the blank areas of the sky flash out with a noise pattern like this here. We'll get to that in a minute as well. Again, the very bright lights are just because the animation can't keep up with me all the time. Okay. Now, oh, now look at that. Did you see this? Right. Let me go back a little bit. Right. Here, I think. And maybe that wasn't it. Anyway, there was a flash in the outer arms only, in the star-forming clumps that are out there. There we go. There. Now, do you see how these regions here and down here lit up like a, I was going to say like a Christmas tree, but you may not be as familiar. Lit up brightly anyway, like fireworks there. Okay, see, now they're only a little bit brighter than the rest of the galaxy. As I go forward in wavelength, look at this. Okay, what we've done is we've hit an emission line, probably from star-forming regions in these outer parts of the arms. Now, another thing to notice about it is, do you see that it progresses from left to right as I increase the wavelength? It first appears in the upper and the left. And then as I go forward, it moves down to the right and the bottom. Going back again. Just like that. What we're seeing is evidence of rotation, or at least a differential motion, where the left side is bluer, the left and upper is bluer, and then the right and the lower is redder by just a few angstroms. Okay. One more thing to notice. Take a look, actually, let's go to the last here. You see this little blob right here, which looks like part of the galaxy. If I were to scan from the infrared back to the blue, watch what happens to it. Still there, but now as I get towards the blue end, it simply fades away. What that's telling us is probably, and because it fades away rather smoothly, it's not a matter of emission lines or absorption lines, but rather it's simply a redder spectrum, and it's probably composed of older, redder stars compared to the younger, hotter stars that dominate the light of the spiral galaxy. Okay, so let me get off of that noisy part right there. There, that's a little bit better. All right, let me create a region here. I click in the center. That creates a region, and what comes up immediately is this window. This is the spectrum, the one-dimensional spectrum of all the light gathered by that circle that I placed there. Now, a region in DS9 language is simply, it's an aperture, it's a little, it is a shape that encloses part of the image. Some of them are just text, you can write on it that way, but others of them are used for doing statistics, which is what we're going to do. So you can click and drag a region around, and we see the center of the region is given here in hours, minutes, and seconds, and degrees, minutes, and seconds of right ascension. Or we can switch it to image coordinates, and it gives it in pixels, X and Y in that case. We can change the radius of the region. We can either hold it on one of those 4 tabs there, change the size that way, or we can go directly here and type in the value that we want, and we hit apply. 0.5 arc seconds. Again, we can change that into other coordinates, like image coordinates, which means pixels. Well, 0.5 arc seconds is precisely 2.5 pixels across in radius. Okay. So let's see what we see with this region here. If you ever cannot find, if you close out that the spectrum, then you can get it back either by double clicking. Double clicking brings up the information in a little information window, or you can select the region, go to the region menu and get information. Make sure it may be behind another window. Once you've selected the information window, notice that it has a number. Every time you create a region, it gets a new number. You go up here, now you have a different set of menus. You go to Analysis and Plot 3D. And you can close the information one and leave the spectrum up. All right, we can adjust the size of the spectrum that way. Okay, this is pretty good. All right, we've got here 3 bright emission lines. Then we have a cluster of 3 very close emission lines, which are also bright, and then a doublet there, and then something way out in the infrared here. Okay, so what are these? Oh, actually, one thing I should do before we go on is I should open up one other that gave me some problems. You want to take a look at the spectral quality before you try going too far into it, because there's something called Telluric lines. And here, let's see, I've already given you the instructions for this part here. Let's go to the next. That's what I showed as well. So does it show strong telluric lines? That's a fancy word meaning Earth atmosphere absorption or emission lines, especially from water, but also from other things as well. So this one doesn't have very strong telluric lines, but I found another one that does. Let's see, I'm going to create a new frame. I'm going to open up this one, which unfortunately is almost 9 gigabytes, and I'm hoping that my computer doesn't choke in the process. I have the disk space to store it in the external drive, but I might not have the memory to analyze them all at the same time. In the meantime, there was a question, how can we open the circle window containing the spectrum? So do you mean how to create the circle in the first place? In my settings for DS9, you can change them. When I click in the image, if you're using a Windows machine, it would be a right click. Let's see, whatever the standard click is. I don't know if that's left or right. It simply creates the region right there. But that may not be the default settings when you download DS9 for the first time. In that case, you would need to go into, I'll have to wait until this loads. You'd have to go into the preferences here in the main menu and set it so that when you click on it, then you get a region placed there. I think I may have made a mistake by trying to open a 9 gigabyte file while I've got a 3 gigabyte file and a 5 gigabyte file already open. That may be too much for it. If that's the case, I'll simply kill this program and reopen it. There actually is in Unix and I guess Linux as well, there's a term which is kill, which is if you have a computer program running, which is taking up all the memory of your computer, you can get outside that and then kill it from a terminal window, or there's another way of doing it on the Mac. Oh, it worked. Okay. All right. This is an elliptical galaxy, so I decided it wasn't really as good for what I wanted here. Now, if I want to create a region, I simply click here. And I have to let it think because I have so many things open. All right. And I get the spectrum. And you think, hey, that's a pretty good spectrum. It shows all kinds of spectral lines, except these are Earth atmosphere lines, most of them at least. Some of them may be, the broader ones here and here, may be from the galaxy itself, also possibly here and here. The trouble is that most of these others are in the Earth's atmosphere. In fact, by the way, we can click and drag in the spectrum window in order to zoom in. Look at that. I'm not a spectroscopist. I mean, I do a little bit, but not enough to be an expert on what lines I'm looking at all the time. But that may be some molecular lines there. And I think, again, possibly water. Very, very regular lines like that. Now, by the way, if we've zoomed in, we hit the escape key to zoom back out. If we zoom in twice, let's say we do that once, and then that a second time, or many more times. We hit escape once, we go back to the previous. We hit escape again, we go back to the previous before that. Okay, so this is almost unusable, at least for an easy demonstration, because it's so completely covered with the telluric lines. Again, you can probably make out lines that are in the source galaxy itself. These stylines are simply identical. There are probably hundreds of them. There are lists that you can come up with. You can find templates of the stylines. Another way is, although I haven't really tried it myself, but you could get the spectrum of a region which is outside of the galaxy itself, say in a blank part of the sky. Trouble is, if the galaxy is very wide, you might not be able to do that. So I'm going to move the region away from the middle of the galaxy, and we'll watch and see. We should still have the lines from the sky, but our broad absorption lines that appear to be from the galaxy. Look at that. The continuum is gone, which was the galaxy, and we're left with the sky only. So now you can see those telluric lines. Isn't this interesting? Again, I need to practice more spectroscopy to figure out exactly how that's going there, but I know I've seen features of that before. You're getting absorption with a narrow line and what looks like broad emission around that, but maybe that's, again, a molecular feature. Okay. So if we drag this back, we go partway there, we should see more continuum show up once it updates that. Yeah, a little bit there. Now we see these are some absorption lines that seem to be coming up, maybe in the galaxy. And then as you go on to here, you wind up back to where we were. Okay, now these skylines probably happen when you have the target closer to the horizon. And so you're looking through a thicker column of atmosphere. But maybe they occur, maybe they go along with other levels of solar activity as well. And I've mostly observed using the Hubble Space Telescope, and I haven't had to deal with them. And so I'm not entirely sure if you can predict always when they're going to be there. But anyway, if it's covered in all that stuff, you might simply go on to choose something else. Okay, so I'm going to close this frame. That'll free up some memory, I hope. Okay, so let's go back here. Now, let's see. So this one does not show. Let's just take the whole galaxy. All right, there's the whole galaxy. Oh, not yet. There we are. Okay, and we see certainly some emission lines. In fact, over here on the left, we see what are certainly broad emission. Possibly that's coming from an active nucleus, because we'd have gas orbiting the black hole, but I wouldn't absolutely swear on it. We have these other lines here and here, and then way out here in the infrared, and what looks like some absorption lines here. We'd have to look and see what's causing that, and here, here, and here. Okay. Now, I don't see really strong telluric lines. Probably we've got some over here. I'm going to guess that most of these are telluric, except for this absorption line. But if we're looking at these bright emission lines, we don't have to worry about them very much. So our next task is to find the redshift of the galaxy. Let's make this bigger. All right. So we want to be able to identify some of these lines. Now, from experience working with quasars, I think I can identify these here is involving the hydrogen alpha emission, and the one to the right is nitrogen 2. And I don't remember what this one to the left is, but it's usually much fainter. These here would be sulfur, a sulfur doublet. And over here, let's see, that may be oxygen 3 and hydrogen beta would be one of those there, but I have to take a look. So you can go and find template galaxy spectra. Now let's see here. Where did I put my template spectrum? Hang on a minute. Hang on, I put this in a different place somehow. I printed it out, and probably that's why I don't have it here. Okay, so let me just go and download it again. Oh. Yes, all right, I put it in a different folder for this talk. Well, that's one of them. This one is a little bit too detailed. Well, it doesn't have all the lines labeled. They label a few of them, but I'd like to see one which has the entire spectrum with all the major lines labeled at once. And I did find that. Here we are. Okay, let's open that up. I just went to the web and said Seifert 1 galaxy template spectrum or average spectrum. And I found this. All right. Now, this is all in the rest frame, meaning the frame of reference of the source galaxy, the wavelength when that light is emitted itself. Notice what you see at around 5,000 angstroms. This, by the way, is at full scale. And then here we have looked at the fainter features. We've not changed the horizontal scaling, but only the vertical scaling here. So what we see, these three lines together here are H beta, which typically in an active galaxy has a broad and then a narrow component. Oxygen 3, the brackets around this mean it is a so-called forbidden transition. That is the meaning that under normal laboratory conditions on the Earth, we would not see this line at all because the gas is too dense, even in a good vacuum on the Earth, to where the atoms collide with each other and you get collisional excitation or de-excitation, and it would prevent that line, that transition from ever happening. And then finally, another oxygen 3 line at 5,007 angstroms. Okay. If those three are, oh, hang on here, let's see. Okay, we've also got these three here. We have H alpha at 6563, and we have nitrogen 2 at 6583. These are very close together, and if you have a very broad H alpha, your N2 is going to be right off on the cusp of it there. And then we've got a sulfur doublet right to the right of those there. Okay, and this may be the oxygen line here. All right, so I'm going to say that this is probably H alpha. That's the nitrogen 2. This is the sulfur doublet. And then over here, we probably got the H beta and what were the others? 2 oxygen 3 lines here. Now notice, they look different. in the template than they do here. The heights of the lines are different, one relative to another. That's okay. That actually does happen in nature because we have different conditions, temperatures and densities and so on like that. And so that can affect the relative intensity of one line versus another. But the positions look correct. Now, the way that we can test this is we can pick a line that we feel pretty confident about. And because we get more shifting, red shifting, the farther red we go, I'm going to pick one that's over here on the right-hand side, like H alpha, which is bright, therefore has a good signal-to-noise ratio. And so I can measure the peak accurately, and then it'll be shifted more than something over here to the left, for example. So I'm going to zoom in on that peak, and I can do this in DS9. It may be more convenient to download the data set. Hold on, let's go back. If you've selected your spectrum, you go to File and Save Data. And it says, ds9.dat. You can label it whatever you want. It is a text file. Your computer might not recognize it as a text file. If you put .dat, you can put it .txt or whatever. And all it's going to look like is hang on. It's simply going to show you two columns, wavelength and intensity, and that's it. And you can open it in a spreadsheet or anything else you can graph with, or you can write your own program, which is what most of us wind up doing. I'm arranging a lot of these so that you can use a spreadsheet for them. Okay, so let's find the wavelength of H alpha, the redshifted version. Okay, that seems to be good enough. We've got it down to 3 decimal places, which is more than the accuracy we can justify. If I go to data set and let's see, graph, and let's see here. Data set and shape, let's put diamonds. And that shows you where every data point in the spectrum is. So if we're looking at that there, you see we can't justify going down to 0.001 angstroms because the spacing of our sample here is not at that kind of precision. 6668, 6669, 6670. All right. So I'm just going to pick this here. Let's say that this is 66. I'll round it to the nearest whole integer, so 6670. Okay, so we write that down. Now we look at our template spectrum, or you should know the wavelength of H alpha anyway. 6563, and so we can calculate this. And I made a spreadsheet out of it here. I copied and pasted the wavelength and the intensity, and I've done some other calculations. And I come up with, here's the formula. The redshift is the shift in wavelength divided by the source wavelengths, delta lambda over lambda. To put it more carefully, the observed wavelength minus the source wavelength. So observed wavelength is what you get out of the spectrograph. Source wavelength is what it is according to the laboratory books. And then you divide that difference by the source wavelength, and that's Z. For low redshift objects, that's approximately the fraction of the speed of light that is moving away from you. However, when you get past a redshift of about 0.3 or 30% the speed of light, then it winds up being inaccurate, and you can actually wind up getting redshifts that are greater than 1. Doesn't mean it's moving faster than the speed of light away from you. All right, now what we're going to do is we calculate the redshift from that one line, and then we want to compare other prominent lines to see if they match up when we use that redshift. And if they don't, then we try and identify it from something else. In this case, I'm pretty confident that I got it right. Once I do that, I calculate the source wavelength for this line and that one, and they match up very nicely with these other two here. And then I go over to these three here, and those match, using the same redshift, those match up with the H beta and the O3 lines there. So that's good. Okay. Now, next thing we're going to do, let me get rid of those dots for just now. Okay, next thing we want to do is take a look as we scan through at one spectral line. Oh, actually, before we do that, just because this has such neat stuff on it here, let's create a second region right there. Now, I told you that there was this kind of a blob over there. And let's compare the spectrum of the center of the galaxy, the nucleus, to the spectrum of that other region. So this upper one here is the center of the galaxy. And then that spot to the right is below it. Let's get the scale about the same. Now look at that. Center and this area on the right. Now, we can't even tell there's anything on that area on the right unless we go out to the red region, down into the far red or infrared. So what do we see? Well, for one thing, instead of bright emission lines, we still get a few emission lines. We've got the H alpha and the nitrogen 2 there. We've got the sulfur doublet as well. But now we've got a lot of prominent absorption lines. We don't get these three emission lines. We get this one here. I think that one's the H beta. Let's take a look again. Yes, H beta and then 2 O3 lines there. I may have misspoken a moment ago. All right. This is H alpha. The middle one's H alpha, and that one is an O. That was a nitrogen 2. So H beta and 2 O3 lines. Now, notice here in the emission part of the center, this H beta is a very narrow line, and these two oxygen lines are a little bit broader there. Not broad lines per se, but a bit broader. Whereas when we look on the thing on the right, we've got the same redshift. If we're identifying, we're identifying the same lines. Okay. Same redshift, but now our H beta is broad, and in fact, it's split there. So there's some emission in a narrow range of wavelengths, and then there is broader absorption on top of that. This indicates that you have cooler gas, hydrogen gas, moving at a range of speeds. So this is Doppler broadening of the line. This is a little blue shifted. The gas here is cool and moving towards you. This here is a little red shifted. So this is cool and moving away from you, but all along the same line of sight. And then you have somewhere in there, you have emission at a narrow range of wavelengths. Okay. We also get whatever this feature is at 6,000 angstroms, and I haven't tried to identify that one yet. We get it deeply in absorption. Here we get an emission line that doesn't appear here at all. Here we get our three lines here with the around H alpha again, and our sulfur. And we get a prominent break here. I've been taking a look at that with some of the rest of this. I'm not sure what causes this either, but it may be, I'm not sure if telluric lines would ever do that. It seems to appear everywhere within the image at some level. Some of this, these narrow emission lines, this could be noisy, or it could simply be telluric lines. But I think these deep ones here are definitely absorption lines that are in the object. Yeah, we see those same absorption lines there. Can't tell about this if that's corresponding to anything there. Sometimes it can be hard to tell what's continuum versus a line and what is absorption versus continuum and so on. It's tricky. Okay, but the main thing to note is at the center of the galaxy, we have the continuum slopes. It's brighter in the blue and is fainter in the red. Whereas in this little thing on the right, the continuum is faint in the blue and bright in the red. And this is a very general measure of the age of the stars there. It could also be a measure of the dust, the reddening from the dust, but it may be age here. So this tells us that we have a different population of stars here entirely from whatever surrounds it. In fact, if we were to look anywhere else in this galaxy, okay, usually it doesn't leave this trace of little circles behind, but I'm using up so much memory right now, that may be why. Okay, anywhere else around here, I do not get the spectrum of what I'm seeing in that region on the right. Which tells me I'm dealing with something distinct. In fact, but it's at the same redshift. So it may be gravitationally bound to the main galaxy, and perhaps it's a dwarf galaxy, which is orbiting around it, a dwarf companion galaxy there. So that's a neat little find. Okay, now where were we? What we want to do is to go to one of the emission lines, and we're going to scan through it. Let's take this one. That is, what was it? That's an O3 line. Let's go to 5080. Now I'm going to find my wavelength selector again. Okay. Now, as we step through the wavelengths, okay, that wasn't quite as dramatic because the rest of the galaxy brightened and faded with that one there. Let's try H beta. Okay, 4930. I'm just going to hit play and then I'll stop when I see it. So watch the image. There we go. That's what I wanted to see. So let's take it back a few wavelengths, a few angstroms. Now, again, this appears to start on the upper left. Okay, we'll go forward again. There. Starts on the upper left, and then it moves to the lower right. So we should be able to put, let's put one region up here and another region. Now let's see here. Where did we get? I've got to find a region that is bright when we get to that. Okay, it may be about right. Okay, so we're looking at this here. Okay. Now, I didn't get these to line up. The grid lines don't line up exactly here, but at least it's close enough to tell. So we can tell that the peak, and let's make sure we see where the dots are so we don't over-interpret this. The proper way to do this would be to fit either a Gaussian or what's called a Lorentzian shape, it depends on what's appropriate, to the shape of the line. On the other hand, we're going to do this a little more crudely and simply take the brightest part here. So let's say in this case, the peak is at, let's see, let's go from there to there. All right. 4395. Oh. Okay. 4940. So the upper one here, 4939.5. And this one here, 4940. Let's see here, 0.5, let's say 0.8, like that. So you can calculate the Doppler shift between those two. Yes, the other question coming in, both spectra are symmetrical. And so you may be able, it may be possible to do a Gaussian fit to them there. That would take a little more software than what I'm doing right now, which is purely doing it by eye. All right, so we can calculate those two things there. Now, we can calculate the difference in velocity between them. So, all right, the difference in velocity. Normally, we would measure this relative to the center of the galaxy, which I did not do in this case here. I was using only one edge and the other. But the speed of material, let's say we label each region with an index number I. The speed in region I relative to the center is V equals the speed of light c times delta lambda over lambda again. But in this case, delta lambda is the wavelength of the peak in the region I that you're measuring minus the wavelength of that spectral line peak in the center of the galaxy. And then we divide by the wavelength of the peak in the center of the galaxy. And this gives us the speed relative to that center. Well, you could do it for any 2 points in there. If we want to do the blue side versus the red side without measuring anything in between, we can simply put one minus, lambda blue minus lambda red, the blue shift and the red shift sides, divided by, in that case, we should really divide by the, let's say the average. It's not going to make a great difference because the difference in the two wavelengths is relatively small, and we're dividing by a large number, which is not much different from one to the other there. All right, and that gets us the speed. Now, in this case, I haven't yet done the calculation for this one here. I was trying to make a full rotation curve for you, and I couldn't get it to work with this particular galaxy. So I'm going to show you the general approach and then show you what a real rotation curve would look like. Okay, and I see it's already about an hour and a half in right now, so I'm going to be wrapping this up soon and have time for questions. Okay, so let's go to the spreadsheet, and I'll just make a scratch page here. So blue side, and we're at 4939 point, let's say 5, let's say 0.6. Again, I can't really justify that level of precision. The red side, 4940.8. That's in angstroms there. So delta lambda would be let's take the longer minus the shorter. And then speed of light c, 3 times 10 to the 8th meters per second. I should make a note here that this is angstroms, that's angstroms, that's angstroms. And then the speed relative is delta lambda times the speed of light divided by, at this point I'm just going to pick either one of them. I really should divide by the average. Okay, we've got a relative speed from one side of the galaxy to the other of 73,000 meters per second. So 73 kilometers per second. Okay, that's not too bad. That's within the range of orbital speeds of the rotation of a galaxy. Let's see here. Yash asks, is the velocity obtained here the z component with respect to the image of the velocity? It is the speed relative to the center of the galaxy, or in this case, the speed of one side relative to the other, which means that if you put either the red or the blue side and consider that to be at rest, then the speed we've got is the speed of the other side in that reference frame. That is, we have completely removed the redshift of the whole galaxy from us. So the Hubble expansion of the universe is gone in this case here. And we're only looking at local motions within the galaxy itself. Does that answer your question correctly? Or in a way that makes some sense? Okay. Let's see. Now, the proper way to do a full rotation curve would be to get a whole lot of these regions. All right, so I can select regions and simply delete them. And I can save regions as files here. I've already done so. So I'm going to go to the region menu and I'm going to load up regions. And it asks me, okay, load in the current frame. Yes, there, like that. So I was trying to do it this way. The trouble is, it turned out that I wasn't getting a very distinct difference in the spectrum from one of these to the next. I think my rotational axis is parallel to this line here instead, and I should have gone across this way. But it may take some experimentation from you. Now, what we're going to do is, for each one of these, we need to know its position within the galaxy. So this is going to be a radial distance from the center of the galaxy in kiloparsecs. Let's go back up here. To make the rotation curve. All right, we could create a set of regions that do not overlap, stretching from blue side to the red side and passing through the center. And make sure that one region is at the exact center. I've done half of this here, and I should continue it on that way. And again, I should have done this at a different angle. Okay, so here I've got one region at the center. And I can show plot 3D. Okay, there's my spectrum in the center. And I can go out to one of these here and plot its spectrum like that. Okay, definitely noisier, definitely bluer as well, maybe. And then I can compare those there like that. Okay, and again, if you download the spectrum, you can do this more quickly, or maybe not more quickly, but with more precision. Okay, but we need to plot for a rotation curve. We want to get the relative velocity of that region, of the gas in that region, versus the distance from the center. So we need to find the distance from the center. So I take the region at the center. I'm going to look at the center coordinates, and I'm going to put them in image coordinates. And that's going to give me X and Y coordinates in pixels. The same thing that shows up here. If you take a look at the image coordinates, X and Y there, which in this case is the same as physical. Okay, we just get those numbers, which it shows. By the way, WCS stands for World Coordinate System. And that's going to refer to right ascension and declination, or perhaps some other system like equatorial, that is equatorial, like ecliptic coordinates or galactic coordinates. Now, FK5 is one standard reference for that there. But that's, again, hours, minutes, seconds, and degrees, minutes, seconds. Okay, so we put this one there in those units. Now let's pick one of these here. Okay, region number 17, I want to keep a list of them. And I put its coordinates in image coordinates there. Well, all you need to do is to use the Pythagorean theorem and convert the distance between them and calculate the hypotenuse between those 2 points. And that gets you the distance between them there in pixels. But we need, okay, region center in pixels, X and Y. Region number 6, for example, is there. The distance, radius R in pixels, and I want to convert that to kiloparsecs. Now, how do I do that then? Well, a useful thing is we can take the redshift of our galaxy, and knowing the redshift, because we've already calculated that, we go to Ned Wright's JavaScript cosmology calculator, which is a very handy tool that the cosmologist Ned Wright has come up with. And for a given set of Hubble's constant, the density of matter, and then an open or flat universe, and the density of dark matter, dark energy, you can put in a redshift. In this case, let's see, I calculated the redshift to be 0.01598. So let's copy and paste that in there. And I'm going to hit the general button. If you type on open or flat, it specifies a particular kind of cosmology. We're just going to leave his numbers at the default settings and go with general. I click on that, and I should update it. Yes, it's rounded it off, but it's got it here. I'd confirm that there. And we're going to look at, this gives a scale of 0.327 kiloparsecs per arc second. That's the double prime is arc seconds. That's our scale to go from arc seconds to kiloparsecs. Now the trouble is, where were we here? I've also got to convert between pixels and kiloparsecs. Let's see, I think I did this part by hand. So we've got kiloparsecs to arc seconds, and now we go over here and we find out how many pixels is an arc second. The easiest way to do it is to select one region, look at its radius. It doesn't matter what the radius is. Here it's given in the world coordinate system and in arc seconds, 0.5. We switch that to image, which gives us the equivalent in pixels. So 0.5 arc seconds equals 2.5 pixels. We take the ratio and we can multiply those two conversion factors to get 1 pixel is 0.0654 kiloparsecs for a galaxy at that redshift. Okay, so now I put that conversion there, and I can use that to convert between pixels and kiloparsecs. Okay, and now I've got all of my regions and I have locations for them here. Now I put the wavelength in the region. I put the difference between the wavelength of that particular whatever the emission line is, and the wavelength at the center, and I calculate the difference in wavelength, and I calculate the speed there, and I didn't get this to come out very well here. I think I was making some incorrect assumptions, or maybe I used a bad emission line, which simply doesn't show up in the same way in all of these places there. But you would have velocity versus distance from the center. Now, let me show you. Okay, that's as far as I've gotten there. Let me show you what a real rotation curve looks like. Okay, let's just put this over here as well. Oh, and I should, let me put Ned Wright's cosmology calculator here in the chat window. Okay. So let's take a look at this one here, for example. It's Wikipedia, I know, but honestly, it's pretty good for this. For a lot of technical subjects, it's a good source to start with. If we look at the speed in kilometers per second, remember we got 75 kilometers per second, 78 for that one measurement. Okay. And we look at the distance from the center, they have it in light years, we'll put it in kiloparsecs. It turns out that when we observe these here at greater and greater distances, we wind up with the speed kind of flattening out. If you go very far out, you have to use hydrogen gas because you can't see starlight out that far. But the interesting thing is that we would actually expect from the visible glowing matter that the speed would decrease as we got up beyond the visible extent of the disk. The reason is, as the density of matter, well, let's just imagine that we had only, if you can see in my camera here of me, if we only had a tight ball of matter in that galaxy, and we looked at the orbit of a single star orbiting around that there. Well, the neat thing about, you'll have to look up Kepler's third law of motion, third law of planetary motion. And it says that the period squared of a planet's orbit around the sun is proportional to its distance from the sun cubed. Newton expanded that and was able to show that it depends on that and on the mass inside the orbit, not necessarily the mass of the star, but the total mass of everything between the center of that star and the planet, and including the mass of the planet. Now, if we expand this to a whole galaxy, you see, a star is very compact. As you get farther away from the star, you're not enclosing any additional mass between you and the star. And so the farther out you are, the more slowly you're going to be orbiting. This is why Mercury takes only 88 days to go around the sun, but Pluto takes over 200 years, 289 years, I think. But in a galaxy, you've got a continuous distribution of matter. So as you're very close to the center, let's take a look at this diagram again, you see the speeds are relatively slow because there's almost no matter enclosed within that orbit. And so it moves relatively slowly. As you go a little bit farther out, it's enclosing more matter within it, and so it orbits more quickly. Now, if the galaxy ended at some distance, like about here, say, on this diagram, then we would expect that stars or hydrogen gas that's farther out, maybe just a little bit, so it's not adding much mass to the galaxy, but we can trace its motion. It would be moving more slowly the farther it went away because it is farther from that mass, like Pluto is from the sun. But what we found was that the rotation curve either keeps on going up, but it kind of shallows out, or it flattens in general. And sometimes it's kind of wavy up and down. What we're finding is that there is more matter out there that's being enclosed, but we can't see it. So this is what we call dark matter. Vera Rubin had worked on this in the 1960s using optical spectroscopy, similar to what you're going to be doing if you choose this project, except with cruder instruments. My graduate research advisor, Stefano Casertano, at the Space Telescope Science Institute, was doing this at the Institute for Advanced Studies at Princeton when he was a postdoc, using 21 centimeter observations of hydrogen gas. And Fritz Zwicky back in the 1930s was doing it with clusters of galaxies, individual galaxies in a cluster, and he found the same thing. So dark matter goes back nearly a century now. You can figure this out as well then. So if we only had the matter that's emitting visible light, we would, or light of any kind, we would expect to see the rotation curve decrease, but instead we see it increase here. Using Kepler's third law of planetary motion with Newton's correction for the enclosed mass, you can say for any one of these rotation points here, you can tell what the total enclosed mass within that orbit is. Furthermore, by regularly spacing out your measurement points, say at maybe 5 kiloparsecs at a time going on out, you can get the differential increase in the mass, which means you take a numerical derivative and you get the mass between these two measurement points, which allows you to get a histogram of the distribution of the mass in the galaxy, which is a really neat result right there. Okay, this is 125. That's the end of my formal part of the presentation. I'm sorry I wasn't able to get a working example of the rotation curve done. Oh, but I did load one more thing before we take questions. Let's delete that frame and that one. And I'm going to show the remaining frames. This one I only have okay, let's give it a moment to load up. It's a 5 gigabyte image here. This is a planetary nebula, NGC 7130, which I think that's a fairly well-known one. I think there's some Hubble images of it. I haven't gotten a chance to look at this yet, but a planetary nebula is a strong source of emission lines, and it ought to provide a really interesting target here. Why don't I see? I'm not even getting the spinning beach ball right now. We'll give it another minute. So you would be able to do things like identifying which gases are in this nebula. You could even determine, with a little more work, well, maybe a lot more work, the temperature of it. You might be able to see the outflow speeds. If you look at from one side to the other, perhaps you'll be able to see the Doppler shift between those two. And in this case, it's not rotation, but it is the expansion of it. So a relatively blue shifted side on, say, well, whichever part is in the front, and a relatively red shifted on the other side there. Trouble is because it's mostly transparent, then you're going to be looking through it. So you're going to see simultaneously the blue shifted and the red shifted parts. If the resolution, the spectral resolution is good enough, you may be able to make out double peaked emission lines then. But I haven't tried this yet, as I said. Why do I not have, hold on. For some reason it doesn't want to show that other frame. Let's see. Okay, there we go. We get a similar coverage and wavelength. Notice how it flashes a lot more here, and that might be because we're looking at very little continuum, but a lot of emission lines. Oh yeah, I've had my students work on this one before. Okay, let's just take a region here. And let's take another one. Notice we get almost no continuum. That's because this is a hot, thin cloud of gas. And so by Kirchhoff's emission laws, laws of emission and absorption, it provides an emission line spectrum. Okay, we have actually got some differences here. You can see there's a little, these lines here. That one is brighter in this here than it's fainter there. Could be just the scaling though. All right, let's take a look at one of these emission lines and see if we see any shape to it. And I'm not seeing any clear splitting of it, and it might just be that we don't have the resolution for that. Except this one here, what's that? That might be showing splitting. I'm not an expert on that though. Okay. But if we were to move that around, over to here, if I could capture this anywhere. Yeah, there are places where we definitely get splitting, and I'm gonna just about bet that that is due to incoming and outgoing gas, so a red shifted and blue shifted gas simultaneously. So yeah, with one that's a nebula that's expanding as fast as this is, you will be able to see that with this resolution, and you'll be able to calculate it. Okay, so this is my brief introduction to integral field spectroscopy. I will make the slideshow available to Priya, and I'll add on a few more of the links here so that you can get started. Also, there's a great little wiki called the Integral Field Spectroscopy Wiki, ifs.wiki.com. Only problem is it is several years out of date. I haven't been updating it much in the last 5 years or so. But for things from 2012, roughly, it's actually very good. And it gives you, the technology really hasn't changed much in the last 5 years. It gives you a very good introduction to the concepts and how you'll analyze the data too. Okay, so Priya, I guess we can turn that over for questions.
Yeah, thanks, Tim, for your excellent signature style.
Welcome.
I myself learned so much. I've never used integral field spectroscopy. I didn't know it.
It's new to me as well, or I guess the first time I used it was about 2 years ago when we got the Keck data.
But it really looks very laborious. Can one actually use Python notebooks to select your regions and do it like that? Because if you're doing it through DS9, it will be crazy, right?
Certainly, I think for any serious analysis, you're going to want to create a Python program for it. Yeah.
Because otherwise, it would be quite a torture doing it.
Okay. But there are Python packages that can help you with integral field data.
Okay, great. I think I should rush on with the questions because there seem to be quite a few. And this is an earlier question, but I think this is somebody asked whether images are seen to be saturated, maybe. No, these are not saturated images, right? They would automatically be clipped, right? I don't think.
You could get saturation in the images. I don't know how likely that is with an integral field unit because you're dispersing the light so much that it would be, you'd have to be hitting a very bright target to have enough light in one wavelength channel to saturate the pixels there. So you're not only dispersing it spatially, but in wavelength, and that helps avoid saturation. In principle, you can still get it saturated, of course, but I think the ones that we were looking at were not saturated, but when you saw the whole screen go bright, that was with one of those atmospheric emission lines.
Mm-hmm. Oh yeah, they could do that, yeah.
Mm-hmm.
I was just thinking of the galaxy. Okay, is the Yash Chaurasi asks, is the velocity obtained here the z component of the velocity?
Now that one I'd tried to answer, but I'm not sure. Oh, actually, no, that was not an answer that I gave. Is the velocity here the z component with respect to image? Oh, I thought I did type in on that there.
Oh yeah, and
maybe it didn't go.
Yeah.
I don't see my reply here. But yes, so when we look at the rotation of a galaxy, then we are seeing, if we compare the velocity, if we compare the wavelengths in two different regions of the same galaxy, that automatically takes out the overall motion of the galaxy away from us. So we're not looking at the velocity relative to us, but rather relative to the other part of that galaxy then. I'm not entirely sure if that was the question there. But we no longer have to worry about how fast the galaxy is moving because of the Hubble flow.
Mm-hmm. Yeah. Can this be used to study galaxy clusters?
Oh, sorry. One other thing, by the way.
Yeah, sorry.
One thing I forgot to mention, and I need to put in the steps here, which I don't have yet, for doing a rotation curve. There's one missing piece, and that may be what the question is getting at, in fact. It is still a line of sight velocity, radial relative to us. And so that may be more of what the question is about. The galaxy may not be rotating in the horizontal plane of the sky. Rather, it could be tilted, in fact, like the one that I showed you is. In that case, if the inclination angle to our line of sight is I, that's the usual letter for it, then we only get the mass times the sine of I. That is, if the galaxy were at, if its symmetry axis, you can see my camera here, we're 90 degrees away from our line of sight, so perpendicular to us, if it's rotating horizontally like that, the inclination angle is 90 degrees, and we would get mass times the sine of 90, which is 1, so just the mass that we would have it. On the other hand, if this is the inclination, the symmetry axis, if it's face on to us like this, rotating that way, the inclination angle is 0, the sine of 0 is 0, we cannot measure the mass then. We get no Doppler shifting at all. If it's somewhere in between, it's somewhere in between. And that's what we're generally going to have. So what you need to do is you need to measure that inclination angle by taking the major and minor axes of the galaxy as a shape, as an elliptical shape. And you can calculate the inclination angle from those. There are better and worse ways of doing it. If it's got very strong spiral arms, it may be a little more difficult, like this one was. It wasn't perfectly symmetrical, and so we might be led astray by that. But if you can fit a model, like with the program GalFit to it, it would give you the major and minor axes and would allow you to find the inclination angle that way. Mm-hmm. And that would allow you to correct for it and get the true mass.
Mm-hmm. Yeah. Thanks so much. So I think that there are no more questions, but in the usual listing, once our workshop is over, I will float a Google form where people can decide which projects they're going to work in. And I guess in the thing, you'll give us a sample list, right? Source list or something like that, which people can select from. Yeah. Mm-hmm. Okay. So thanks a lot, Tim. Thanks so much for your session. And sorry to keep you up for so late.
Well, I'm glad to be able to do it then again, and hopefully to get to see you all in person sometime.
Yeah. If you're coming to Busan, we should hopefully meet. Are you coming to the General Assembly?
Okay, right there.
Okay. So thanks so much. And like I said, you can select your project once the workshop is over. Yeah.
Oh, and one last question. There was, can we measure how much dark matter is in a galaxy? Yes, but it requires extra steps where you have to measure how much visible matter is in the galaxy first. You take the total mass you get with this, subtract the visible matter, you're left with the dark matter. But that's a good project, but it does require extra analysis.
There was a version of that done earlier, right, in our earlier sessions, which you remember you have done it. Yeah.
Yep.
Yeah. Okay. Fine. So thanks a lot, Tim. Thank you so much. Thanks, everyone.
You're welcome.
Yeah.
Right. Thanks, everybody.
Thank you. Bye.
Goodbye.